Our second important form of energy for this course is kinetic energy. The roots of the word kinetic, you've heard of this before. I'm assuming anything with this sort of kin means moving. So kinetic energy is the energy something has just by the fact that it's moving. Like moving air makes a turbine spin in a windmill. The moving air had energy to turn the turbine. Anything that's moving has the energy. It has the ability to do work on something it bumps into. It has the ability to put a force on, has the ability to push something around if it bumps into something. Energy also ties into work. In this way, it took work to get it moving. If we built a little robot that was going to push bowling balls around or push whatever around, every time it pushed a bowling ball and got the bowling ball moving, the battery pack of our little robot would be a little bit drained. It takes work to make something start to move. We could, if we want to get crazy, tie that back to like Newton's laws, F equals ma. Takes a force to accelerate it. If you're accelerating it over a distance, there's your force and distance. That means work. Again, we don't have to do proofs in this class. There's a kind of another little cool proof for kinetic energy. Kinetic energy ends up having a half in it. Kinetic energy depends on the mass of the object. If something's really heavy, it takes more work, or the heavy thing has more energy once it's moving. And kinetic energy, hopefully, obviously, depends on the speed. Turns out that it depends on the speed squared. So if we push something to a certain speed, it's going to take work. If we push it to double the speed, because of the square, it would take 4 times as much work. If we push something to triple the speed, it would take 9 times more work. Putting that out of word language into math language, kinetic energy is 1/2. Short form for mass is m, and speed is v. So 1/2 m v squared. That's our equation for kinetic energy. That one will be posted on or typed on our equation sheet once we get to the point where we need that. Let's say you could Google it. 2,000 kilograms isn't ridiculously heavy for a car. 20 meters per second, you can practice it. Maybe off in the margin, practice it. What's that one in kilometers per hour? Um, it's not a crazy fast speed. Like you're driving on a big street, maybe not a subdivision street, but definitely slower than highway speeds. You can practice what 20 meters per second is if you want to put it in kilometers per hour just for context. Kinetic energy is 1/2 mv squared. I tried to make up, maybe we can do some mental math here. 1/2 of 2,000 is the m. That's going to be 1,000. Then we got to multiply that by 20 squared. So the 2,000 and a half make a 1,000. 20 squared is like 4 with 2 zeros. And then we had the 3 zeros of the 1,000, so we get this number, 400,000 joules. We could put it in scientific notation if you want to make it fancy, but I'm okay just leaving it as 4,000. Is that fast? I don't know if anybody tried it. If you tried it, no, it's not crazy fast. 20 meters per second is a nice clean one. The magic number is 3.6. We have to multiply. So 20 meters per second is 72 kilometers per hour. Not crazy fast. It's a normal sized car, if anything, maybe a little bit light, and it's not going crazy fast. 400,000 is a pretty big number. It takes quite a bit of energy to get a big heavy car going at that kind of moderate speed. Where did that energy come from? That's a trickier question nowadays, but that came from the gas in the car or the battery if you have an electric or a hybrid car, but something had to give it that energy. And then the bad news is when a car stops, where does that energy go? If you've got a gas car, that energy's gone. Oops. That energy's gone in a gas car. We don't really, in a gas car, there's no mechanism to get that energy back. The brake pads get a little bit warmer. But it's gone. Like we can't recharge a gas-powered car. In a battery-powered car, there's this thing called regenerative braking. So if you've got a hybrid or a battery-powered car, they can actually take the kinetic energy and use some of it to recharge the battery. It's not perfect. It's not, the word we would use is 100% efficient. It's not 100% efficient, so it doesn't charge the battery all the way back, those 400,000 joules, but some of the energy goes back into the battery, recharges it a little bit. That's kind of the big benefit of electric cars is you can kind of recharge themselves as you brake, so the energy just doesn't go completely away. Okay, another one. What if we've got, I don't know, bowling balls on the brain when I was typing this up? If we have a bowling ball with a particular amount of energy, we can figure out how fast it's going. Kinetic energy is always 1/2 mv squared. Jamming in our numbers, it's really basically a plug and chug. The EK was 90. We've got a 1/2 here, 5 v squared. Doing a little bit of math on this one. Let me just check my numbers. I would multiply the 2 over, so I get v squared equals, multiply by 2, 180. I would divide by 5. Calculator work. I got 36. That's v squared. To get v all by itself, we need to square root both sides. The square root of 36 is 6. If we want to be fancy, matching the question, it needs 3 digits. So 6.00, and that's in meters per second. Okay, that's just a little short video clip. We'll stop this one, and then we're going to move on to conservation of energy, kind of combining those two together.